Okay, so good afternoon, everybody. Welcome to the final talk of the Deep Learning Barcelona Symposium. So this talk comes a bit late, actually 1 year late. Oriol was supposed to be our final speaker last year in the symposium, but unfortunately there was a drone flying over London airport, so he couldn't be here on time. But this time he flew quite much earlier, so he was already here yesterday to make sure that he could be ready for the talk. So probably you know Oriol, but I'll just a brief bio. He studied at UBC in the CEFIS program for the Teleco and Math program, and then he also graduated for PhD on Berkeley, and now he's a principal research scientist at Google DeepMind. And he's got a very extensive work, but today he'll talk about his quite recent Nature paper from cover on StarCraft. So thank you very much, Oriol, for coming, and also thank you very much for trying to take care of the community. So while you are in London, Oriol is of course trying to help the local community in make deep learning grow here at home. So thank you very much. So please a big round of applause for Oriol Vinyals.
Thank you. Thank you. It's truly great to be here. It's always so special to come back so close to UPC, where it all started, although, you know, I also then forget about where my high school was and so on. So I'm from Sabadell, and I come from a small school there that's called San Nicolau. I studied at UPC, and then I went off to the US, but now I currently am in London. And actually, before beginning maybe the formal talk, I would like to say a few words about kind of the topic that Xavi was alluding to. The first one is that, so you might have seen this. This is sort of representing the world and scaling each country proportional to the number of NeurIPS accepted papers, I guess. And there clearly are two continents, Africa and South America, that are quite misrepresented. I actually was very fortunate to attend a month or so ago in Montevideo in Uruguay, Quipu, and there I realized the amount of effort that it takes for you to build up a community. So, you know, we can see we're there a bit like a sandwich, maybe. You can kind of see where Spain and Portugal are, and we're about here, I guess. So I don't know if we're small, but clearly also there's a lot of work to be done. So I would start really by thanking the organizers of these events. The local community here has been really great at receiving me, but here the true heroes are those who are organizing. So I would just like to ask for a round of applause for all the amazing organizers. I've been really kind of experiencing the growth and the efforts that are making sort of Barcelona grow as an AI center, and I'm excited for the future, but a lot of the work really goes without saying that is from the local people that have stayed here and haven't left, or maybe have left, have come back, and so on. We are, of course, all trying to participate and contribute. And on that note, I have a few words before I start talking about video games and reinforcement learning. First of which is that we do really have, at least I experience, amazing universities, and in particular the undergraduate program that I did prepared me really well for what was to come. And maybe if I could talk to my young self, I would say focus on building up your curriculum and research, perhaps not on your grades. Now, I'm not saying minimize your grades, okay? If you're a student, please, that's not what I'm saying, but I'm also saying not only maximize your grades, right? So this is something that you only kind of learn later, and I wish someone had said it as clearly as I'm saying it to you today. And the other, I think, is kind of given, is try to live in a different country. I think this is an enriching life experience that if you can, you should try to do. Now, moving forward, it's true, Barcelona as an AI hub would be great. I think there are some key elements that are just unchangeable from this city in terms of environment, culture, nature, and so on and so forth. And perhaps two things that I also see a lot of progress is, first, the language of science seems to be English today. Maybe in a year or 100 years, I'll be saying learn Chinese, but today it's English. So I am very happy to see that we can make these kind of events and be English kind of the sort of the vehicle for communication. And the other one is that it's important in our country to emphasize excellence. I think it's important that this word elitism sounds like a bit bad sometimes, but truly, if we take the very few of us who kind of are very passionate and become quite experts in some fields, as a country, as a community, culturally, we should really see this as a very good thing and try to kind of help a lot, which again, I'm seeing some signs of life, but more can be done. And then maybe the last and not least, though, is that even if you're not a student and you're not maximizing grades or whatever you're doing, it's important to always think for yourself whether what you're doing is what you really want to do. I started doing deep learning when it was not a hot field, but I really liked it. So I wish for everyone that is entering fields today, including deep learning, that does so at least partly because it's something that you really like and you're passionate about. So these are a few things, and I will just say a fun anecdote that my nephew, who is 11, is here. He doesn't quite speak English, but Alex, tu explicaré casa avui. Lo que estic dient. Okay. So let's get kind of serious into kind of research and the kinds of things that we've been doing in the last few years. The mission of DeepMind is to solve intelligence, use it to make the world a better place. And one way in which we do or propose to do that is with the reinforcement learning paradigm, which probably most of you are familiar. So we love to see this kind of agent environment loop, which is kind of very pure. It allows us to put neural networks on the agent side, receive observation, issue actions, and kind of hope for the best, right? And this has worked surprisingly well, especially in certain kind of environments. A lot of more progress has to be made, but this clearly is a formula that has worked well for others, and of course also for DeepMind. And perhaps the thing that put deep reinforcement learning in the map for me actually was the paper from Vlad et al. That was actually presented at NeurIPS in 2014. There was a workshop that crucially, I guess, or significantly, Mark Zuckerberg attended because they were launching an AI lab. But for me, and this was actually, I think it was 2013, but anyways, maybe 2014, okay? Don't quote me on this one. But in that workshop, actually, for me, the most significant result and kind of the thing that I will remember forever was that Vladny explained this very cool benchmark of playing Atari video games with a pure learn approach, which to me was magical. It was well beyond, all these data set, accuracy improvements, and so on. So I really liked this at the time. I just started my career at Google Brain in California, but later on I obviously joined DeepMind and I became part of this kind of understanding and enhancing this paradigm of deep reinforcement learning. So a few years after, actually I joined DeepMind maybe 3 months before the Lee Sedol matches that AlphaGo played. So I was very lucky to see it from the office at 4 a.m. in London, but it was quite intense, hard to sleep. Or fall asleep, even though I have no idea about Go. It's a fun game, though, I hear. But anyways, if we look a few years forward, right, the point of using these games is just to kind of use it as a benchmark for how advanced really are these neural networks at playing and excelling at tasks that we humans picked up as interesting enough tasks for us that we played many years cumulatively, probably millennia. And certainly Go kind of pushed the envelope in a couple of key aspects, one of which is that Go is a multiplayer game. You play against someone else. This is quite important because it makes for this magical symmetry that even if you become very good, you always could play against yourself. So there's always kind of very marginal ways in which you can improve your game. And the other is the action space. So the branching factor of Go is about 300 or so, which is higher than Atari, and of course also higher than chess and other games that are very related to this. So now I get to talk about a game that I used to play as a kid as well, and I have a simple question for the audience. So who here, let me see how I ask this, it's important. Who here has not heard about the game of StarCraft and doesn't know what it is about? Okay. I'm gonna still explain about the game, but I'm just curious. Okay, because we have some videos later, so okay, maybe I'll go through those as well. So this is a video game. It's in the real-time strategy genre, and the game consists of several objectives or sub-goals that you as a player must do at simultaneous rate. The obvious things you do is collect resources. That gives you money, gas or minerals. You, with this money, can build a base and expand to perhaps collect more resources. You also can build units. The units you build are important because eventually you're going to encounter the opponent, and if you defeat all the buildings of the opponent, you win in a 1 versus 1 setup. And hopefully the internet is good enough for this video to load. Otherwise, we'll skip some of the videos, but let me see. Am I connected, actually? I am connected. Let me try again. Oh, it just loaded, of course. So that's Google Slides always requires connectivity, not surprisingly. So this is kind of a zoomed out version of StarCraft, and here you can see kind of what the board looks like. It's kind of very much bigger than chess, right? It looks that the units, these things that move around, are much smaller than a chess piece would look like. And crucially, you see that we have a base here at the top left. There's some workers that are collecting resources. Now we're going to expand or create a new building over there. But then there's also some units we have at the bottom. These units are scouting, right? They're trying to reveal information from the other side, from the enemy, because in StarCraft and many other games, you don't get to see what's going on the other side of the board, right? So StarCraft is a bit like chess, but you start with very little amount of units. You need to decide at all times what units are you going to build, and also at the same time, you don't see the other side of the board, so you need to go and scout. And also, interestingly, when you zoom in into a player's view, again, if the video loads, I'll try it a few times. Maybe if I do this. So anyways, if you zoom in, you actually, the interface to play this game is not quite like I showed you. It's almost, it looks very natural interface, like where you drag and drop. It's like when you use Mac or Windows, right? You have a mouse, you have keyboards, you have shortcuts and combinations. And crucially, you are supposed to move the camera around to build your buildings wherever you want, right? So this player here is sort of panning or moving the camera. It's kind of building new workers, selecting things, building some buildings at the ramp. And you can see at the bottom left is kind of the zoomed out view that I was showing before. And so what this player has to do is figure out what's happening in the enemy, but also building stuff. And obviously, the skills required to play this game are also quite high. So in terms of complexity, StarCraft really adds kind of a few dimensions of above what was done in Atari and Go. It's quite complex, especially in the information aspect. So as I was saying, we don't see all that that's happening always, so there's imperfect information. And perhaps the other element that I really like is that the amount of actions, if you consider all the almost key combinations, mouse combinations, and so on, it's really, really, really high. So that is very challenging for many reasons that we are about to see. So, of course, this links back to DeepMind's mission because this acts kind of as a benchmark on solving intelligence. We want to solve some games that are more and more complex, that challenges our intellect towards this goal. And also the kinds of actions and being in real-time game and all sorts of aspects makes this a bit closer as well to real-world problems, right? So in a way, we hope that this is advancing on both ends. And actually, StarCraft, as a domain for research, has been proposed actually by many others before us, and it's only that in 2016 or so that we became engaged with the game producer, and we actually open sourced the environment for research, but a lot of competitions and activities were going on dating back to 2010 or so. And in fact, when I was a grad student at Berkeley, we built a bot that played the game of StarCraft I as part of a almost summer project, and that bot was kind of rule-based, right? It was using mostly knowledge about the game, and it was if-else kind of agent or code that runs the game. And of course, many things have changed. But at the time, also, Dan Klein, who was the lead of that project, was teaching undergraduate students AI through StarCraft, and he has these class slides where he kind of mentioned, well, StarCraft has many challenges, real-time, long horizon, partial observable, and so on. And it had this quote that I truly believed, and of course, at 2011, this was really true, that no single AI technique could solve such a complex game off the shelf. But what's kind of magically happened is that there is now a single neural network that is playing this game at a pretty good level. And I'll explain a little bit, pieces and here and there, about how we actually built this agent to play this complex game. So things start to get interesting as well when we have to also understand that this game is played by humans like the one on the left here. Now I'll try to higher the volume. Maybe it's not outputting anyways. So you would hear frenetic amount of clicking, like click, 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 like very fast, because people, of course, train to play this game professionally, and they can issue about 400 actions per minute, right? So that is many actions to the game about like moving units around, building fights, and so on and so forth. So of course, it is very hard to define the parameters for which an agent should be limited, so that we believe that it plays the game at sort of equal grounds to the human players that we intend to play. Of course, we're doing this or thinking about this before even agents start to do anything reasonable, so it's pretty tricky. And of course, doing it with robotics, the classic video on the left here is the robots falling video. You've seen it so many times. But it would be a bit tricky, although my very good friends from Berkeley probably are thinking about this with these robotic arms and so on. Hopefully, we could interface with the game and play the game of StarCraft through the actual interfaces that we humans use, so as to try to understand the motor control and skills and accuracies that are involved. This video is very recommended if you haven't seen it. It's really, really fun. It's a bit old, but I'm not sure anyone can argue that things are much better than this, although things are a bit better than this, okay? So let's be very bright now. I guess this is research mode, so these slides will be a bit whiter, and I'm going to talk to you about, you know, I showed the others ones in video game conferences, so they're very, like, you have to see those conferences that look like this room, actually, which is great. More contrast, less people sleeping. So anyways, I'm going to describe, and we're actually going to go quite deep into some aspects. I've given this talk a couple of times, but there are a couple of things that, as many of you probably are training and using deep learning day to day, I wanted to kind of almost empathize from a large-scale project like this, that many of the things you're suffering, we suffer too. So no spoilers, but you'll see what I mean in a few slides. Now, first, of course, we have to explain what is this one single algorithm or agent that plays the game. So I'm going to describe a bit the actions and the architectures that we designed and use to play StarCraft. Then I'm going to explain how we solve exploration. We've heard a lot of behavioral cloning and imitation learning in this conference, so no surprise there. That's a bit of what we did as well for the project. And last, there's a very interesting component in this game that self-play, you know, having these agents playing against each other, doesn't quite make the agents as robust as we would like them to be. So I'll explain what we devised as a solution for that. And of course, there's fairness that I just described that makes the problem harder, because of course, adding limitations to the agents makes the problem harder by definition, because you cannot express the same policies that you could if you had unlimited action clicks per minute and so on. On that note, once an oracle gives you the weights of a neural network, this is what AlphaStar uses and plays the game. It's, again, the loop of observing the game. There's a few observations like the minimap, the units, and the opponent units, and so on. There's a single neural network that, in this case, does not use any search. It's simply computing a single GPU. I'm not sure which GPU it is. It takes about maybe 30 milliseconds to do an inference. And at the top, it tells you what the action to be issued at this time step should be. This is then filtered for these fairness issues that I was discussing. So we're going to limit the action rate should the agent decide to do too many actions per minute, or maybe to be too precise, and so on. We send this action to the game. The game interprets the action, runs, and so on. And importantly, this is a game that is real time. So when we train, we can, of course, pause the game and say, oh, let me think about what the move should be, and go ahead and send it back to the game. But when we played online against people, we couldn't possibly pause the universe. So what happened is that there was an obvious delay for all the processing that is needed that we just had to deal with. So we didn't do anything fancy or special. We just hoped for the best, that this delay would not affect us too much, and it didn't seem to affect us too much. But in real time, when you issue your action, it might be that it goes to the engine definitely a few milliseconds and a few game loops behind, which obviously is not ideal, but of course people also have delayed reaction times, so that felt reasonable as well. And I'm going to describe again parts of this algorithm, but this paper was published a month and a half ago or so in the Nature magazine. So I invite you to, of course, read the paper, read the supplementary materials. There's lots of things to cover and lots of details there. So obviously, take a look at it. If you have questions, you can obviously always email the authors. We'll be happy to reply to your queries. And let's move on to actually seeing some of the components in more detail. So how do you issue actions in such a game? From an agent perspective, right? From a human, you clearly are just doing some keyboard-mouse combination. And what those actions generally look like are something like this particular action, right? So this group of 7 units is issuing this crystal magical thing that blocks units from walking through them, which is actually interesting because you block this ramp with this wall so that maybe enemy units cannot enter, so you have some time to think about how to react. And this particular issuing this force field, as it's called, requires several decisions to be made, right? Several sub-actions. Obviously, we need to decide what is the action that we're going to issue. That is force field, right? Then who is issuing this action, right? What are the set of units amongst all the units that I have that I'm going to instruct to issue this command to? And in this one, you see we have these 7 units selected. So the who is 4 of these sentries and 3 of the stalkers. Obviously, not all the action combinations are valid. And that's something that we could either, with domain knowledge, restrict to the kinds of actions that only for the kinds of units that we have and so on. But at the end, we actually didn't do that. We just allowed the agent to issue any action to any subset of units because, of course, there's a lot of knowledge from imitation learning that we gather, so we don't need to filter, so to speak. Then there's a where element. Where in the map are we going to put this unit or this force field? And in this case, it's on the ramp. And then critically, we need to decide when are we going to observe the game and act again in the future. And that's also something the agent must decide as it's issuing all the actions once, for every time step of the game that it decides to act on, right? So in this case, it might say, look, I'm going to wait a second. If it didn't wait so long, maybe it also increases its action rate, which is not a very good thing to do. So it waits maybe 1 second, and then it will observe the game and decide what the action should be. So that's essentially how an action is built in the game of StarCraft under. This is pretty much what the game engine sends through not the neural network, sorry, I was about to say to the network, to the actual network, the Telecos network, the cables, to communicate with the other client that is running the game. And this is what maps the inputs to the outputs, the inputs observations to these actions, and I'll explain these components. What's nice here is that all these components are very natural choices if you've been in deep learning research and you know how to encode certain data modalities, right? I'll try to give you the intuition for each of them, but they should feel quite natural to all of you. The observations. Okay, we have a few features that are just scalars, right? These are how much time has it been since the game started, how many minerals do we have, how much gas do we have, etc. And for these, we just simply use MLP, a deep neural network, multi-layer perceptron, very standard. We also have entities. This is a set of units, both our units and enemy units. This is an order set, and I've seen some cool posters talking about the difference between sequences and sets, but a very natural way to encode a set of objects is to use a transformer. It's the current state of the art for many of the tasks that we love about sequences and sets. So that's how we encode these entities through a transformer. And last but not least, we have some sort of spatial or visual input, which is the zoomed out view, the minimap that users see. For this one, we use a deep ResNet, which is, again, super standard component in any deep learning framework. And last but not least, we just concatenate all these learned representations onto a deep LSTM, which acts as a memory. That being said, you could also use a transformer as memory, and it's work in progress to make that work well for this domain. But because of speed constraints and so on, we use a simple LSTM as memory element here. And then the part that I really like, because it's very natural language processing-like, is how to generate this sequence of instructions or actions that compose every single StarCraft action that must be sent to the game. The way to do that is, again, by applying the chain rule of probability. There are 10 to the 26, more or less, possibilities of subsets of units, what these units can be, where the action could be, and so on. It's a combinatorial space. It's too large for you to say, well, let's just do a flat softmax. I mean, try it, but it's not going to work, okay? So what we do is we just simply decide for a sub-action, and then given the first sub-action, decide the second sub-action, and so on and so forth. And we have an autoregressive small head at each time step that we need to decide what to do. That's outputting each of these data types that needs to be output. And of course, this is generic. Any computer API that has a complicated structure of actions, you can always decompose it with sub-actions, use the chain rule to provide a joint probability distribution that is going to be properly trained, and then that is your policy that maps inputs to outputs. And there's a couple of these that require attention. The first one is softmax over the what to do. There's maybe 200, 500 options in StarCraft about the kinds of actions. We sample these, we embed it, we decide when we're going to do the next action. That's just how many time steps are we going to delay. Also pretty simple. But then the one that I really like comes in, which is we have some units. It could be 20 units, it could be 200 units, and I need to pick a subset of these units to which the action it will be issued. And to do that, we use something very natural in deep learning, which uses pointer networks and just recurrence over that, right? So the idea is very simple. You start with an empty set. You decide what's the first unit that you're going to issue this action to. You point to it by an attention mechanism, essentially. Now, given the first unit that you just pointed at, you then point at the second unit with the same mechanism, and you do this for a few time steps. You unroll this process perhaps 100 times or so that you can cover most actions that are reasonable in StarCraft. And then eventually you point to a special embedding that says, I'm done pointing. This is a subset that I select to issue this action to. After which, you just then go to decide where, which is a simple decompnet if you require spatial coordinate, or a unit, perhaps your own units or enemy units. Maybe it's a spell that you have to cast on top of a unit. And this whole process essentially is what the neural network is about. And of course, the magic of how we train these weights is all we care about. But this, by design, is no assumptions made about almost anything. It's very generic components. Of course, they're very interconnected in smart ways, which as deep learning engineers or researchers, we all must do. So if you have a question about this, that would be a good time now, or we can do it at the end as well. But any question about the AlphaStar architecture, the neural net behind the agents, and so on? Yeah, over there. Mm-hmm. Yeah. Yeah. Right, so that's a great question. This is about, it's an interesting bit, right? You're deciding when are you going to do the next action, but what if you change your mind and so on? Let me maybe dive a bit into this detail, which is pretty fun, right? So first is like the action that you're building up. All this action is going to be issued right now. Not really right now because there's a bit of latency, but this is the action that under the current observation, it looks like I must build a worker. So that's the action I'm going to issue. But the agent is deciding when is the next action going to be. A next action which is to be decided whenever the next observation comes. But there's an important detail, right? You mentioned 5-second delay. I mean, in 5 seconds, some things could happen. And actually, the agent, this particular agent, is blind to whatever happens, right? So it might be that you decide, oh, it looks very peaceful. I'm going to wait 5 seconds and then look at the game and see what happened. And some things that are bad could have happened before 5 seconds, in which case the agent has to deal with it whenever the new observation comes. Of course, this is a fairly fast-paced game. Generally, you observe the game fast enough that you wouldn't miss key things, but you could miss some key things because you're kind of, it's almost you close your eyes, you open, you act, and then you close them again, which is not how humans play exactly, but that seemed reasonable. But great question. We can get more questions at the end as well, or over the break. There's the value network. I'm going to skip this. OK. So how do we train the weights? And one of the things that happens in this game is that the issue of exploration is really, really, really hard. The action space is very large. So the probability of doing a sequence of sensible actions so as to do the obvious things you need to do in these kind of games becomes vanishingly small, right? Just think about the clicks, the precise click sequence that you would need to issue to create another base. Let it finish, you cannot cancel it, and canceling is an action that our agent sadly takes sometimes. Sometimes not well done, sometimes it needs to cancel buildings. But you have this base, it needs to be built fully, and then once it's built, you must create workers that start gathering resources. These resources increase your economy, but the reward we're using here is just about winning the game, right? So imagine how weak of a reward it is for this sequence of actions that has 10 to the minus 8, but that's a very kind of generous bound, right? So exploration is a challenge which we really didn't solve in a perhaps elegant way, but I think we solve it in actually a way that most humans would agree with, which is you just look how other people play and you imitate what they do, which is a topic of research that I really love, which we've heard many talks about imitation learning. But let me just show you what happens if you try pure self-play without any priors. What happens is agents decide to attack with the workers. So these little things were pulled away from mining. You would say, well, I'm not sure what to do with this money anyway. I have no clue about this game. Really, you're clicking randomly in the map, issuing actions at random. Most actions you issue are hurtful. Most actions will take your workers away from work, and then good luck placing the worker properly into the minerals that are close to your base. But what the agent quickly discovered is to just go with the workers. Now your enemy is yourself. You're pretty bad. You don't know how to defend against these. So this works. This gives you a reward. And this keeps improving this strategy again and again. And you get into this deep optima of play, which is, not surprisingly, humans play like this. I mean, if you just don't know anything about the game, you might win against some very bad players. But it's not really a very nice way to play the game. And it shows a lot of these exploration issues that we face in the game. But it's very obvious that this happens, right? With some probability, you send a worker to attack at a round where the enemy is. If you don't pull it out, eventually you get a reward, you reinforce it, and so on. As I was saying, though, we were very lucky that Blizzard, the company that made the game, is actually every day, today, yesterday, and so on, opening many of the games that people are playing online at basically global scale. So this is a very large, actually, sequence modeling data set that there's an API. You can just go and maybe download thousands, tens of thousands of games per day. And we collected, for a period of time, a data set of essentially how humans play this game in the way that you would do language modeling, right? Which again comes back, I really like language modeling. So the idea of behavioral cloning is as simple as, look, humans have observed the game up to time t. They have done some actions up to time t. Just encode, embed all this information, like observations and previous actions, and compute or maximize the probability of whatever the human is going to do right now. And that's it, right? And you have a long sequence, you do maximum likelihood training, and you see what happens with the agent that you train like that. And the short story is this works. The long story is it is very hard to make it work, and I'll explain you the long story. But from a zoomed out view, what this caused is that in this metric that we have a set of held out agents. We never play or train against these agents. These serve as kind of a metric for how good AlphaStar agents were. As we were developing them, we couldn't possibly play online all the time. It would be too costly. So no human data, the kinds of strategies that you saw before, get 100 ELO score, and supervised agent without reinforcement learning, simply trying to emulate or pretend to be a human gets you 900 ELO, which is very strong. 400 ELO difference is about 90% win rate. So if I'm 400 ELO higher than you, I win you under like 0.9 with 0.9 probability, right? So, this is a big difference. And then we do other things that maybe I'll skip to explain, including this Z conditioning, but we can chat about these offline. But this is super simple to do. We have a lot of data. And again, if you want to think how machine translation works, it's exactly the same. There's a sequence of words that are English, then a partial sequence of French, and then you predict the next word given all you've seen. It's the same model. It's kind of almost boring that it all works the same for all these domains, but it does. And so here is when we get into the details, right? So the story wasn't just that we kind of designed this architecture on a whiteboard, and then we went ahead, we trained it. It takes maybe 2 days to train this architecture. It's not that bad, and voila, we get an agent that was 900 ELO score. Of course, we were learning about the problem and developing the architecture, and so that took a bit of time. If you look at the simple built-in bots that Blizzard has put, because we don't play or train against them, they're actually a good, reasonable proxy metric that we used early in the project. So the win rate, percentage of wins against the elite bot is what I'm showing here. The baseline was at 0%. I mean, and 0% obviously is very bad. It's not that, I mean, the first jump is very substantial because when we added this predicting the delay of the next action, which before we were doing just play at a constant rate, it tremendously improved already the way that AlphaStar was playing. And then we added all these elements that I was describing, like pointer networks, transformers, scatter connections, and we got to a fairly high win rate only from supervised learning, which also we calibrated online, and we showed that result later. But how did that happen, right? And these are the things or findings that we were just kind of brainstorming with the team, and many things that seemed to be good ideas that didn't work, and the face here should tell you kind of the things that worked, right? So, you know, big, deep LSTMs work, but convolutional two-dimensional STMs didn't work. Gradient clipping, which is a thing that many people do, actually didn't seem to help very much, and so on and so forth, right? So there are the architecture itself, which you saw in the previous slide, but also all the amount of detail that goes into training deep learning models, which, believe me, you should know about. If you don't know about, you should really learn about them, and it's not the most pleasant experience, I must tell you. And this is a bit of the process that also, it looked a bit like an ImageNet challenge in itself, right? We have this problem, we have a metric, let's try to build an architecture and tune it so that we get a better metric. In this case, perhaps we were even looking at the medium bot, which is not as good as the elite or very hard bot, right? So the initial condition was, again, 0% win rate, and medium bot was perhaps 6%. But then we started, increasing the dimensionality of some observation, adding gated connections, making the LSTM bigger and deeper, and so on. And this is just the very first iteration of early experiments. Eventually, after more iterations, we got to a performance that, if plotted, would be up here, right, of 90% or so win rate against the very hard bot. So this is a long process. And believe me, everyone has to go through this, even though you might not hear it on all the talks. So just don't despair, this is normal. Okay, now that being said, we have this awesome policy that has been trained with imitation. What do we do with it? Well, the very first thing you might be tempted to do is, okay, it's about 900 ELO. Let's just use self-play, right? Like initialize our neural network, get it to play against itself, add this pure reward of winning or losing, and see what happens. And what happens is not much. It improves 100 ELO, which is not a small amount, but actually the kind of same effect that we saw before happens. That is, all the strategies that it learned from supervised or imitation learning kind of degenerate to a single strategy, which is not as bad as the worker rush, but it's not very good. And so the diversity of the policy, if you will, is lost, and this becomes a not very robust policy. It's a very kind of unimodal way to play the game. What really worked well was to add a distillation cost. That is, we encourage the policy throughout training to not diverge too much from the initial condition. That is a very simple thing to do, and it really worked well. That made the ELO score jump by 400 by 400. So adding that loss there at the top helped. And the last, which I'm not going to have time to explain, is to add this form of sort of high-level or hierarchical way to play the game, which added about 100 or so ELO. We also have did some tuning in the RL algorithm itself. Again, details perhaps to look at in the paper, but maybe one that I really like is this one, which is, in StarCraft, you're not, of course, allowed to see what's happening in the other side of the map. But your value network, the network that is trying to predict who is winning this game, well, it might be useful if you're trying to predict the winner to know what the enemy is doing, because you'll be more accurate at predicting who is ahead. And that's what precisely we did, and we verified that if you give privileged information only to the value network, which during play you're not going to use, you get a massive reduction in variance, which increases, in this case, an average win rate against some opponents by a large margin, and we never looked back. I mean, we did this a while back in the project, and that was the default setup. So last but not least is that these agents, despite good, they still had a lot of kind of robustness issues. Like you would play against them, and if you did some funky kind of original strategy, they would really not be very good. The last agents we have, they lost some games, but obviously they improved a lot through this idea of training them, much like we train when we play online on the online service. So when you play this game online, you're not playing it only against yourself. You're going online and you play against your friends, or you're not friends, and you many times observe or are exposed to very new strategies that you play against once, and then you play again, and maybe eventually you learn the strategy yourself, or at least you learn how to defend against that particular strategy. People, even today, after 20 years of this game existing, come up with new strategies all the time. And our agents were not doing that process exactly like how humans have discovered this game. So what we did is we empowered self-play with this idea, which actually is very similar to something that we do sometimes in supervised learning, which is we have the main agents, they are playing each race, they're playing against everyone, and they're trying to win. That's the goal that we give it to them. But we also have a new kinds of agents that we call exploiters. And these agents are very particular. These agents essentially are just going to obsess with beating one of the main agents, right? So I'm just going to play games against that particular agent, against no one else. I only care to win the main agent. And at the same time, the main agent is not going to be shown how that exploiter plays for a while, right? So it's like as if I played against you, and I let the reinforcement learning reward teach me how to maybe beat you, but you're not allowed to update your brain or parameters, right? You're kind of a frozen agent. I get to observe how you're playing, try to exploit you, and once I succeed, once I win you some amount of time, maybe 70% of the time, only then I will place myself in the league. I will tell you, okay, now you can play against me, and you'll need to figure out how to beat me because I'm beating you 70% of the time. And then I go again, and I try to exploit the main agent again, right? So it's a bit asymmetric. It's a bit unfair to the main agent because the main agent is played against, and it cannot learn anything from those games. But it creates this idea of like robustness against exploits that you might encounter online. And it's a bit similar to how you would do adversarial robustness, right? So it's almost like you have a neural network, and you find what's the optimal input so as this neural network is maximally confused, right? It's a bit like that, but in reinforcement learning. And there's some more details, of course, that I'm skipping here, but that's the intuition. And these amazingly work. So this video shows a main agent in blue that is being exploited by the red agent, and the blue agent cannot train its weights against the red agent. And what the red agent discovered is that you can do these cannon buildings close to the base of the blue person, and just the blue agent just hasn't received too much training against this particular kind of cheese, as it's called in StarCraft, and it simply fails to win, right? It's just like, it's an exploit, you find it, the red agent becomes really good at it against the blue agent. Eventually, red agent says, this is how I win, and now the green agent, a new main agent that has been training for a long time, actually discovers that it must build these zealot units that are very early defensive units, and also even pull all its workers to defend against this early threat. And this keeps going for a while. For a while is for a few days of training, 44 days that we train these agents. And against a held out set of exploits that we kind of designed as a test set, we saw that this procedure actually helps a lot, and all our agents kind of became better and better against these sort of exploits that certainly we would encounter online. So that was a way to add robustness that, again, when tested in terms of ELO score, added another 300 or so ELO to the main agents, and that is what is AlphaStar, right? These all like two building blocks that I just explained. Now, a note about training time is that, well, DeepRL is not data efficient. There's no other way to put it, and even to play simple games like Atari, like Pong and so on, it might take, the current best agents I ask around, it's about maybe 1,000 hours of playtime per game. And this is a game that you need to learn that the ball needs to not pass and you just need to hit it, right? So it's pretty complex even for those games, or long. In AlphaStar, every single agent, the main agents, were run for 44 days, but of course, we were able to accelerate real time. So those 44 days translated more or less to 200 game years, which is a lot of StarCraft. It's pros play a lot of time. I mean, I don't know, I didn't ask this, maybe I should, although maybe they wouldn't answer, but how many game years, like this is literally playing for a full year nonstop, no sleeping, no eating, would a professional player play? I assume it's no more than hopefully 4, but who knows, right? But clearly this is above expectations, and nonetheless, these agents start from random weights, or they use actually imitation. So there's a lot to do in data efficiency. And from a technical standpoint, we're very fortunate to have, of course, a very nice infrastructure and engineering team at DeepMind and at Google, which allowed us to train these agents using TPU devices. This is a bit what the overall training or infrastructure looks like. There are learners that are running on an 8x8 TPU subpod, I guess. So these hold the weights of the neural network, and then they receive trajectories or batches of experience from which they update their parameters using essentially Impala or Actor Critic updates. But we need to separate these from the actors and the game, right? The game itself, StarCraft, is not a very cheap game to run like chess would, which is kind of almost 2 lines of code. So the environments are running on CPUs. We have maybe 8,000 CPU cores running the game at scale. And the goal of these workers is simply to produce observations, send them to actors that are gonna quickly, so this is batch size 1, return the action to be done on that observation, and the loop kind of is created, the observation action loop is created here, and then these actors are sort of batching experience. As we know, batching makes hardware use much more efficient, so we use large batches to be sent to the learners to update the parameters, and then of course we have a job that is computing the statistics of who is winning against whom in the league, because we need to do that to run also the multi-agent algorithm that I just described. And how it looks like if we zoom out and we take a real picture is something like this. So these are the TPU pods that we have in data centers. I haven't visited one yet, but I should. It's pretty beautiful. And I hear the one we run maybe has a plaque or something that says AlphaStar, but I want to visit that. But anyways, these are pretty high flops and very energy efficient. And as we know, GPUs, TPUs, and specialized hardware is here to stay. And I'm very happy to see also lots of efforts done locally by BCC and so on to get into these, the large hardware requirements that these algorithms generally need to run. So let's go very quickly through the results. This is obviously fun, but it's not as hard to explain perhaps as the algorithm, which I wanted to make sure at least some of you that might have seen some of these is now clearer, right? So we went through 2 stages, one of which was playing against a few professionals, but we had a different version that was not as restrictive as the current AlphaStar is in terms of actions per minute. And we had a long cast. I am here, I think, yeah. So anyways, you can scan that or just go online on YouTube and see this stream. This is from January. And since then, we went to play all races of StarCraft. Back then, we only played one single map, Protoss versus Protoss. So right now, in order to play online in the wild without modifying the gamer experience on the other side, we play all races and 4 maps, and then we play, crucially, under more restrictive limitations, especially at peaking actions per minute. Back in January, we had a very reasonable action per minute rate, but the agent discovered that in certain occasions it could spike up, it could do many actions, and it would go above what people deemed reasonable. So we make sure that under short bursts of actions, the agent couldn't go above some limit. And adding that, basically, and iterating with TLO, who's been consulting for the project since January, we arrived to a pretty good solution, which we put all the games online, and pretty much people, well, there's obviously still discussions about what fairness means in these kind of situations, but clearly we didn't kind of break the game and made maybe Rock somehow better than Caesars which is kind of what happened in a way on January. And also, crucially, we added a camera element to the game, which is as simple to say as that instead of perceiving all the units all the time that we could see, not the ones that are under the fog of war, we now actually have an agent that must also at the same time move the camera around to gather information, which is actually makes it for a very pleasant viewing experience. People that have seen replays from AlphaStar, like this one, AlphaStar moves the camera in a way that is not as spammy as professional gamers do. Of course, this came at a cost, and we lost about 10% win rate against the built-in bot when we went to camera interface, but that was a necessary kind of loss of accuracy, or in this case, performance, to be fair. So what happened was very cool. I didn't imagine in January we could be able to pull this off, but we kind of convinced Blizzard to let us try these agents in the service online. And we asked players, hey, do you want to maybe be matched against AlphaStar? We'll play anonymously as best as we can. And most people opted in, so they had this menu, and they clicked opt-in, and that happened, I think, essentially 80% or more players opted in to play potentially against AlphaStar. And then we played a series of maybe, with all races, maybe 300, 400, 500 games or so. And we started sort of climbing the ladder from what you start at, which is a ranked ranking. And you play against people at your own level, and then Battle.net is matching you against people of your own level, and if you're getting more and more ELO or MMR, then you will be matched against higher and higher players. So maybe AlphaStar ranks usually around here. That's the maximum ranking you can get if you win 5-0 your placement matches, which all of our agents did. And then eventually, as it played more games, it ranked in the Grandmaster League, which is the higher league, only reserved for the top 200 players, and above about 99.8% or so of all players that played in Europe, actually. And what's very cool to see is that as we were experiencing this ourselves, the researchers, we put the agent online, and the first person who played had no idea. And at the end of the game, that person also had no idea, right? So in a way, it's very nice to play the game at a very high level, but it's also very nice to pass a sort of Turing test where you're playing against an agent, but you don't quite know that you're playing against an agent. And people discovered eventually after 3 or 4 days, people are very smart, and Reddit is a very useful tool for people to get all sorts of ideas. So they found out, we knew this, that the agent didn't use control groups. And so post-talk, after you play the game, you could rewind the game and observe that, well, this player is kind of playing at really high level, but it's not using this obvious tool that every human would use. So that's how people discovered the identity of AlphaStar. But anyways, that was fun. And to me, also the Turing test part was really cool to see. And then another very nice thing is that the supervised agent that I was mentioning ranked above 85% of players, right? So this agent that doesn't know what win means, it just tries to click the button that the human clicked, it actually plays reasonably well. It's a fun agent to play against. And we actually, in fact, played that agent later as well in BlizzCon. So let's look at a few moments in games. This is the AlphaStar view, so you can see how it's moving the camera. This has this unit. Obviously, it's going to be hard. I mean, it's playing at high level, but it's kind of panning the camera in and out of this kind of harassing unit. It's trying to gather information and get some economic gain by perhaps trying to poke the workers for this Zerg player, which happens to be TLO, actually. And at the same time, you see the agent goes back to the base, it moves the buildings around, it keeps building workers. Now it's checking the third base, it sees there's a third base there, which is now discovered in the red area. And essentially, you can see kind of the process of an agent playing from the agent's perspective, right? What it's looking at, what it's building, and also a bit what the game is about. Later in that game, there's a very tense moment of typical Terran versus Zerg, which is, well, the agent, let me reload, see if it works. Yeah, okay. So the agent now is pushing, right? What it means is the agent has now, you can see the game evolve. This is not the agent's perspective anymore. And the agent is trying to really get into the enemy base and try to start kind of poking into workers, but also figuring out whether it should retreat or not. In this case, it decides to go back. It's doing all these decisions with essentially a neural network, as I showed, right? There's nothing else here. We don't understand its decisions all the time, or like them, rather. But, it actually plays the game reasonably well. And this is a very kind of long struggle that the agent is going through. which eventually ends up pushing into TLO's base, and then he eventually resigns this particular game, although he obviously has won also many other games, but this is the one that he told us was interesting. We didn't ask for wins or losses, but this is an interesting decision-making process of pushing in and out of a base and so on, which is very complicated and requires very high-level understanding of what's going on in the game. We also love how other players reacted. Kelazur, who is a pro player from Brazil, said that also there's some creative play. So that's also another thing you might ask. I mean, okay, it passes the Turing test, but does it really play exactly like a human? So this is another video which you can go and see later, which is a very beautiful commentary by Artosis. And we don't hear the noise, but it's okay, like his voice. But what he's saying is that this unit composition AlphaStar is doing is it works. I mean, he understands why AlphaStar is making it work, but no one else would do this composition. It's the first time he's seeing this particular composition of units that have certain abilities that complement each other and counter what the opponent is doing pretty well here. So last bit of kind of news and results that I wanted to tell you is that first, we went online on Battle.net and we played anonymously, but then obviously we wanted to kind of give to the community the opportunity to come and play against AlphaStar. So we went to this conference in Los Angeles in early November, where we had a few events, but probably the most cool thing we did was to put AlphaStar to play against people. You can see here at the top AlphaStar. We have 20 machines. They're pairs of machines. One is a Windows that runs the game. The other is a Linux machine that runs the agent. We had this in the Google office close to Santa Monica. And then the event happened in Anaheim, which is some kilometers away, right? So this was all magic of connecting all these machines. Actually, it worked. It was a pretty kind of manual process. And we asked people to come in and play. And we had essentially the whole weekend about, depending on the time, but 15 or so machines of people experiencing playing against an AI agent, which is actually quite nice to see, right? Like online, no one really knew maybe at the time they were playing, but here you see kind of the creativity and what people are wondering about and how they're playing. So it's very nice to see kind of AGI in the wild, if you will. Many people lost, but also some people won, and it became a trend to put the victory screen on Twitter. So here, Jacqueline, she posted this snapshot of like winning against AlphaStar Basic. We had 2 levels of difficulty. One that was about Diamond, the other one which was a mixture of agents, but mostly Grandmaster level. And then perhaps the highlight of the weekend was that when Cyril came, Cyril is one of the strongest players in the world, so he just kind of pinged me on Twitter and said, hey, like I want to play against the agent, and we said, sure, like come in, and it was kind of a very cool moment, very interesting community to interact with. So he played, many people were excited to see that. In fact, they were so excited we managed to get these games commented by Artosis, so you should go and check them out. It's also a very nice way to get an introduction to the game if you haven't seen many games recently. And to me, the coolest part of the whole project comes to this, right? So Cyril, a few months later, played in a competition, and in game 2, he tried the same build that AlphaStar had done in Zerg versus Zerg, which is not kind of a traditional build that you would do. He lost. I saw the game. I think he didn't lose because of the build, but anyways, he lost, disclosure. But I really like Juan Pablo's comment, which is kind of saying, well, AlphaStar used imitation learning from humans extensively, and now perhaps the pro players which have access to all these games might learn something also from AlphaStar. So it's almost like there's all this knowledge, we use imitation learning, we improve it with AlphaStar League and self-play, then we give it back to the players, and now they might learn something about their game, which is, as I said, quite exciting thing and prospect for AI agents and in general game playing and other environments that we're interested in. So to conclude, I'm not going to extend too much. I want to leave some time for questions. But to me, the surprising element, perhaps the most surprising from a machine learning perspective, is how good imitation learning is. It really is remarkable. I mean, it beats me. It's really a good agent. Anyways, I'm not as good as I used to be, but still. And it's also model-free, right? There's no search. We don't use like tree search like you do in Go or chess. The agent sees the observation, has a forward pass. It obviously has memory and decides the action on the spot very quickly. So this can be run very cheaply on a GPU. Now, I'll skip this, but I want to leave you with some maybe future-looking perspectives on reinforcement learning and machine learning in general, which is that this is still an environment which we can run very fast, and we have run many copies of the game in parallel to gather 200 game years experience. But it's great also to see or to start thinking, how do we make better simulators that mimic the real world, although that might be as hard as to solve the problems we're about to solve, right? So maybe simulating friction in robotics will be harder than actually going ahead and having our grasping policy, right? Who knows? But it's really, really hard to simulate the real world. And then a very fundamental problem that we see in deep learning over and over, that many, many people out there are also reminding themselves about, is that these agents, the methodology is very generic, right? All these pieces of building blocks that I described, they're all generic building blocks. You're using them in vision, you're using them in NLP. But the weights we train, they become very specialized to the kinds of tasks that you work, right? So these weights for StarCraft, they don't work in Atari at all. And similarly, when you train an ImageNet model, it cannot recognize MNIST, although that for us feels, oh, that's so simple. Of course, I mean, the best ImageNet network certainly knows how to classify MNIST well. I bet you if you just upscale MNIST and pass it, it doesn't even know the classes, right? So there's a lot of work to do in transfer learning, which I am excited to kind of think about and be kind of pushing the envelope for the next few years of research. And last but not least, reinforcement learning is very cool because it has this property of non-stationarity. As you become better at exploiting the games and the environment, you get into new situations you've never seen before. And I think in terms of theory and even building blocks, we probably are just scratching the surface of what's possible. So with that, I'm happy to take more questions, but thank you for being here. Muchas gracias.
So thank you very much, Oriol,
Thank you
for your talk. So as he said, we have time for questions.
Yeah.
Thank you very much for the talk. Very, very cool. Is there any plan to deploy AlphaStar on actual tournaments with professional players, or on the built-in tournament service that Battle.net has?
Right. So that's a great question. We thought about deploying, I mean, obviously it's a very nice training tool even, right, for people to play against. The only problem, which I did not describe, is that the game has different versions and patches, and it changes all the time. So keeping it kind of up to date would be costly. And right now we don't have plans to do that. And I actually talked, we had, they have also amazing results on the game of Dota, as you might have seen from OpenAI. I was just chatting with them literally a few days ago in Vancouver. And they also mentioned the problem that as the game changes, I mean, you need to at least train a little bit, and that creates a lot of kind of overhead. Which goes a bit into the transfer learning question, right? It would be great if you just change the game and you say, well, look, this unit, no one likes this unit, I'm going to make it, it's gone from the game. The agent, of course, will not play very badly, but it needs to be retrained. And that's one of the problems we have right now for expanding or extending its lifetime, if you will. Cool. I saw some other people.
Yeah,
maybe.
who was?
Well, there's behind there.
Okay, sorry.
Yeah.
Sorry.
Hello.
Hey.
First of all, as an ex-StarCraft master player, I really impressed how AlphaStar plays, and I also watch the games before coming here.
Awesome.
Thanks a lot.
Thank you.
For this. This was my childhood dream to see this.
Yeah, my childhood dream as well. I used to play this game a lot. I mean, like my sister is here as well. She can tell you, but I used to play a lot. Anyways, other stories.
Okay, so I have a question about this exploration.
Yeah.
So if I'm not wrong, AlphaGo started as imitation learning as well, and then it switched to self-play, and it really improved its performance.
Yeah.
I know the branching factor here is really, really big, but do you have anything about like pure self-play in the future for AlphaStar?
Yeah, so that's a great question. Obviously, AlphaGo, the first paper really was imitation plus self-play, which we've seen the kind of ELO improvements we get from that. So the same observation applies, and I think this is generic. If you have good imitation learning data plus fine-tuning with RL, do that. I mean, there's no reason not to do it. But playing from self-play from scratch, I think fundamentally, I mean, it feels like very hard to believe, mathematically even, that you could discover these long sequences without adding any prior knowledge, right? So you might be tempted to add pseudo rewards, which we also heard about, like, oh, like, well, look, getting more money is a good thing, so I'm gonna add you a bit of signal so you don't just go and attack with your workers. So there are things you could envision to do to help pure self-play, but then you're adding knowledge from another side rather than imitation, and at least imitation is about learning. Now, that being said, in Go, branching factor and search was great. I think it would be, probably it would take us some time, but it's a great domain for us to explore, like AlphaStar 0, if you will, like no human prior, no pseudo rewards, just play this game, go and try to be as good as you can. It worked. I mean, it gets to worker rushes and so on. So maybe we're not that far, but I think fundamentally we'll need to wait a few years, but it's very cool problem actually. So since you play StarCraft, maybe you should come and work with us on that. You know, yeah, it's a hard problem. Cool, more questions? Let's see, yeah.
All right, so congrats on this brilliant work. So this is arguably a very, very complicated system, and a lot of effort went into that. So going back to one of your earliest points, would you really argue that this is like a single AI technique that solved this problem and it works off the shelf? So like if you would try it on any other real-time strategy game, would it work you know, similarly well, or would you need like extra tweaks on top of this?
Right, so that's a great question. We really try very hard to make all the components as general purpose as possible. That's a word that appears on and on the Nature paper because it's very important, right? It's not so much important about the what is this about getting like good at StarCraft, but the how for us is very important. Now, there's of course always like restrictions, right? So under certain conditions, for instance, I would say, if you have an environment which of course you can accelerate, you can simulate at high speed, and in this particular project, we needed the expert data, and we needed a lot, not a lot, but we had like a few. At the end, we used maybe 100,000 games to learn from to get the initial seed. So these are like the preconditions. These are not game-specific, but not every environment has them, right? I mean, like some people might have access to, let's say, self-driving imitation learning data, but it's not readily available. Under these conditions, however, if you can imagine defining the agent interface, right? The input observations is almost like a description of, oh, there's these modalities, and one is a set, the other is a vector, the other is an image. And then the actions, which can be any computer API, that's precisely what StarCraft is. It's just an API, a function, it's a set of function calls. If your environment can be set in this framework of input modalities that are well known and probably span now almost all modalities you can think about, and the action spec is API-like, then this approach, I think, works. I mean, it's also restricted to 1 versus 1 setup. So there's some caveats, but they're fundamental from the game. None of the building blocks that I describe, I think, are very specific to the particular game, but there's some specificity, of course, to especially like, the zero-sum kind of thing and so on. It's a great point, though, and I mean, it tells us that the how or the algorithms, sure, we're seeing kind of progress and transfer on that regime quite a bit. Also, you can take some component here and make it work elsewhere. I mean, the league or the ideas from the architecture probably are also quite universal. But yeah, it's an important problem and one that we really kind of by principles try to obey that. But sometimes you get a shortcut and okay, let's just do this so that we get there faster, right? But overall, we didn't do almost any of that here, I would say.
So are you by any chance working on like deploying this on other games, or you cannot tell right now?
Well, I can tell you that the answer is no, we're not working on that.
Okay,
would it be cool? Of course, yeah. I mean, video games are nice. Cool. Any other questions, or otherwise, I think there's some closing words from Xabi, but maybe one last question from someone who hasn't asked, ideally.
So we'll take these two that they were around. Who was you?
Hi, thank you for the talk.
Thank you.
I was wondering if DeepMind has like, in the nature of solving intelligence, like is it only through reinforcement learning, or is there like a timeline of, okay, this is how far we got, we're gonna try other techniques, or?
Yeah, I think there's clearly, maybe I remove a word and then I'll say mostly, yeah, we do that, which is learning, right? So learning is the key component that if you look at our research, very much almost all the research and solutions have some learning. Learning scales better than handcrafting. So that's very strong belief, not only from us, but from the community or from a community. Not all the communities might necessarily believe in that. Reinforcement learning, I mean, I come from a supervised learning background. I joined DeepMind kind of to learn reinforcement learning, I would say. So that was my way to learn it through doing a hard problem. And it's part of the puzzle, but pure reinforcement learning, my belief right now is you need other things like imitation learning, and there's ideas here in evolutionary strategies and so on that are also quite interesting. So the answer is not only reinforcement learning, but learning, yeah, you see very strong biases from pretty much all of us that do research there.
Okay, so I'll take the final question.
Okay.
Hi, thank you for the very nice talk.
Thank you.
So very quick question, something that you just mentioned. So that your model is limited to 1 versus 1. I'm interested, do you experiment in, I don't know, 2 versus 2, 4 versus 4, how the agents collaborate with each other against maybe humans that are intentionally collaborating and like trying to work together?
Right, so the game mode we studied, and there's a good reason for that. It's because the game has been just balanced around 1 versus 1, is 1v1. You could totally apply similar techniques. In fact, there's beautiful work done elsewhere. I would say, of course, Dota 2 is a team game. There's also Capture the Flag paper that is very nice collaborative team game that you can see other papers, very extensive papers on both of these. In StarCraft, we did not try. What we tried a little bit is to kind of have agents work with humans, so you can just totally play, kind of override the agent's moves if you want and kind of see if the agent can help you. But we didn't do that very seriously, just kind of, it was almost a bug actually, that you can play the game when the agent is playing. So we said, oh, let's just play the game as the agent plays. But we didn't take, in this project, we mostly focus on, yeah, the pure 1 versus 1 setup. Cool, I'll be around. I guess we can chat later, but thanks a lot. Thanks.
So thank you, Oriol.
Thanks.
Yeah, so if you just allow us 5 more minutes, we'll just close the symposium. So first, start with the acknowledgement. So this symposium has been possible thanks to different institutions that you can see here, the logo. So we try to make it as much diverse and open as possible. We're putting a lot of effort on that, and that's kind of, when we build the program, that's something that we took into account. And we think that that's the right way to build the community, and that to make it, hopefully next year we're going to have like more institutions participating in it, okay? And apart from the organizing institutions, we also had like some very kind sponsors that would like to address some last words. So from Facebook AI, I think you have some words. From Pierre Liu. Yep.
Yeah, yes, just quickly, I have very little to say after this amazing talk from Oriol. Just saying that I've been attending this event, these 2 days, and I have to say that you did an incredibly good work for setting up this agenda, incredible people here, and just remind you that we are a fast-growing lab in Europe and in the US, and you are welcome to apply, and feel free to contact me if you need to need information about that. Thank you.
So, thank you very much. So we've had the chance to enjoy this awesome auditorium on personal, and I think that Jordi Luca, I guess, yeah, he will like to address some final and closing words.
Well, just to say that has been our pleasure to host this symposium. Again, thanks a lot to Xavi for pushing us, all of us, to make it possible, right? And just to say, just continue learning, don't stop, never learning, and don't forget to teach the others, right, what you learn.
Thank you. Okay, whatever, never mind. So now some more final words. I hope there. So could the volunteers stand up for a moment? We had some awesome volunteers. Could you please all stand up? You are more of them. So yeah, they deserve. So there are some there on top as well. Okay, so you don't see them, but they are there. So thank you guys. And as well over there, okay? So this couldn't be possible without you, okay? So we all thank the chairs, and we are very happy about it, but obviously there are so many people who have collaborated here. Then what's coming next, right? That's like kind of one of the questions the chairs pose to ourselves, like, okay, so we have this nice symposium, like, what do we want to do with that? So one of the issues we have is, like, we saw that there's, like, it's kind of hard to know what's going on in the city sometimes in terms of deep learning. And we know that we have those universities and even companies now, they are holding like these super nice talks, and we would like to improve the communication in that. So that's why we have our new mailing list. Hopefully you receive an email with a link there that if you want, you can join. So you should have received an email from Eventbrite. If that didn't work, you can still go to the website and there's a link there and connect, and you can join from there. And also we're going to post it on Twitter later on the link, okay? So you just put the email address there. We're going to announce, like, hopefully the new symposium next year. And if there are other events organized from at least from institutions that we are already organizing this, we're going to post them there so that you can participate. And following like Jordi's advice of keep learning, okay? So we have our Twitter account that maybe you have been following. We did our best to post pictures and updates, and also thanks to all the other Twitter users who were mentioning us and taking pictures. I tried to follow as much as possible through links, but thanks for all these people who are participating online on the community. Okay, and also in the same email from Eventbrite, did you receive anything? Yeah, okay, great. So there's a short survey. If you can provide ideas of how could we make it better and what you like from this symposium, that would hopefully help us for the next edition. Some conclusions here. So after this symposium, that's the second year that we organize it, I think we should all be aware that there is high quality research, like world-class quality research in the field of deep learning. And that's something that sometimes we are not that aware. And here you have like some figures. So here I collected like just the talks, and I started counting venues and conferences. So the actual figures are lower than this, because this means that these are talks that they were talks or no keynote talks at all, and that were presented in the Deep Learning Barcelona Symposium, which of course there were like many other publications that we couldn't bring them all because we didn't know or for other reasons. So I think that we should all be aware of where we are, and hopefully that kind of grows our confidence on the kind of research and motivates us to keep working on this direction. So just also like to be aware that who we are. So the community that we are trying to target with this symposium, we are the local researchers. So now we have, traditionally, we have been publishing from academia, and now also lately we've noticed that also industrial labs, like for example Telefonica, is publishing very high impact quality conference, which was not, maybe it wasn't that normal some time ago, right? And now like there are all these academia and industrial labs who are working on this. So that's one part of the researchers. Also, I'd like to mention all the researchers who couldn't be in the symposium because actually they are local researchers, but probably they come from abroad, so they were born abroad. This Christmas time, they are back home, so they couldn't attend here. But actually, we organized this event on these dates, so that just do the opposite, so that people who maybe they studied here, they are abroad, and they can come here on during their holidays and present their work. So actually, thank you very much to all of those who are actually on holidays and come here and explain your work to the community. And finally, also like to thank, like I know for sure that I have like many of undergraduate students here. I hope that you enjoyed, that you got motivated by all this super nice work of people who have followed your path in the past, and maybe hopefully that enlightens you, like motivates you to follow this research career, at least in this field or in any other field. But you see that there's people who have done it, who have and are doing very nice and enjoying the work a lot, as you can see in the symposium. What else can you do? So you have all this merchandising. We've put this thanks to the sponsorship from Facebook, so we could manage to have all these nice T-shirts and badges and stickers. So we encourage you to wear them with pride in your lab. You can put sticker on your computer. You can wear the badges, or if you go to conferences, maybe you can wear the T-shirts and badges. So that's what we invite you to do. So people are aware, like we have at least very nice badges in Barcelona, and we have all these nice papers. What else? But there's quite a lot of material downstairs still to go, and we need to give it away, right? So I mean, there are people in Telephonic, but not enough to take all of this. So when you leave, just take as much as you want, okay? In a kind of sustainable way. Just give it to your friends. Hey, there was this super nice event. People who are abroad, just bring them. Wow, deep learning in Barcelona is super cool. So bring it to your labs, to your advisors, and that's it. Oh, but don't take this away from you, because hopefully we're going to organize more symposiums. We're trying to reduce the waste. Okay, so just if you want to, please keep this downstairs. We collect it and going to use it in the next symposium. So what's the next symposium? Someday in May, which I don't know yet which day, there's going to be something, I don't know, we call it symposium or whatever, but we're going to have Yoshio Benjo giving a talk, and we haven't organized. We just know that he will speak. We don't know if we're going to do anything else, but just as you are going to join this mailing list, you will be informed as soon as we know where and when he's going to speak, but he's kind of confirmed, right? So hope to see you all there with Yoshio Benjo, or next year in the symposium, wherever we do it, hopefully in a larger venue that can hold everybody without any problem. And that's it. Merry Christmas, Bon Nadal, and happy 2020.